To complete a lab assignment, do every task in the lab report outline. There is one-to-one matching between the list of tasks and the lab guide app items. This Lab 4 assignment is about the op-amp model with negative current feedback IFB, via resistor RFB. As discussed in Part 1, Step 1.3, given the infinite open-loop gain approximation, the op-amp circuit acts like a simple voltage amplifier where the output, Vs, is linearly proportional to the input Vx by a constant factor that is the ratio of two resistances, the feedback and the input. Along the same line of discussion, an issue is whether the simple linear amplifier model, which is derived for steady-state condition, is applicable to time-dependent voltages. The discussion of Part 1, Step 1.3, states that it is incorrect to extrapolate a steady-state causal relationship as shown here, to time-dependent voltages. In other words, the simple linear equation is correct for constant input voltage Vx, but cannot be correct with AC voltage Vx. Hence, the study of this Part A is not just about the validity of this voltage-dependent source model, but also the limitation of the model, that is, the conditions for which the model is no longer valid. Part A is straightforward. First, build the circuit, then perform a systematic series of measurements as shown in the table for step A2 to A7. This is the circuit schematic, showing 3 selectable feedback resistors for 3 gain values. Gently rock back and forth, side to side, to insert the op-amp onto the breadboard. Avoid bending the pins. Connect pin 7 the op-amp to plus voltage supply, and pin 4 to minus voltage supply. The power should be off, of course, but make sure the wiring connection from the breadboard to the power rail is correct. Hover the mouse over the op-amp for pin assignment. Connect non-inverting input pin 3 to ground. Connect the 1 kΩ input resistance with wire to the inverting input pin 2. Put in feedback resistor 1 with wire connected to the op-amp output pin 6. Connect also a wire from the inverting input pin 2 to a location near the feedback resistor, but not to connect to it. Later, we will use a jumper wire to connect to the different feedback resistors. If you have a multi-position switch, connect the wire to the input position on the switch, while the feedback resistor should be connected to a switch position, such as position 1. Put in feedback resistor 2 with wire connected to that of feedback resistor 1 that is connected to op-amp output pin 6. Put in feedback resistor 3 with wire connected to that of feedback resistor 2 that is connected to op-amp output pin 6. The circuit is ready to use. The input should be connected to the split end of a coax cable. The center conductor should be connected to input resistor node, and the ground conductor should be connected to the op-amp ground. Same with for output. To select a particular feedback resistor, connect a jumper wire between the inverting input wire terminal to that of a feedback resistor. This is to switch to feedback resistor 1. Switch to feedback resistor 2. Switch to feedback resistor 3. This is an example of an op-amp voltage amplifier breadboard circuit. Yours need not be exactly like this one in the photograph. Apart from the power supplies, plus and minus 12 to 15 volt and the ground, the key connections to the op-amp chip are pins 2, 3, and 6. The input resistor is connected to pin 2. The feedback resistors are connected to pin 6 and pin 2 via a jumper wire. Pin 3 is connected to the ground. Measurements on this table, from A2 to A7 are best done with the DG lent AD2. The hardware setup is the same for all the steps. Only the input waveforms are different. In fact, detailed examples of many measurements on this table are shown in another video that will be shown later. Next is the recommended approach to use the AD2. It is recommended to use the DG lent AD2 for measurements, also for the convenience of saving data. Use a 6-pin connector as suggested to be the interface between the AD2 cables and the voltage amplifier. There are 3 connections between the AD2 and the circuit. The AD2 signal output, wavegen 1 or 2, is connected to the input end of input resistor R1. Channel scope 1 can be tied to the signal output wavegen 1 near the 6-pin connector, and only one wire connected to R1 is sufficient. The other scope channel, channel 2, is connected to pin 6 output of the op-amp. Once the hardware is set up, except for the occasional change of the feedback resistance jumper wire, the rest is done via the computer interface. The various measurements can be done by controlling the wavegen signal waveform, and the data from the 2 scope channels can be saved. This diagram shows the recommended AD2 connection. This video has detailed instruction how to capture output from the AD2 scope channel 1 and 2, how to export them into CSV files for processing. This screenshot shows the amplification of a 2 kHz sinusoidal input, the yellow scope trace, giving the output, blue scope trace. It is straightforward to measure the ratio of the 2 signal amplitudes to determine the gain, and the phase is obviously 180 degrees to the eye. However, the video shows a utility software that can determine the amplitude and phase with rigorous statistical estimation using the least square fit method. Hence, the user is strongly recommended to follow the guidance given in the video. The following shows an example of a typical measurement. The input signal is set up with desired properties, such as frequency. AD2 data length is about 8000, select the time base such that there are roughly 32 to less than 256 cycles in the displayed scope trace. Then hit Export button, select CSV format and save. The work here is not just to acquire the data. It is essential to understand the rationale and objective of each measurement. It is not critical to follow the exact numerical values of the various waveform parameters such as frequency and amplitude on the table. If you use the software utility mentioned above, it will compute the actual frequencies, amplitudes, and relative gain and phase between the input and output signals. However, you should still read these values from the scope displays to exercise both the learning of using visual assessment as well as for a sanity check. Do not mindlessly and blindly carry out the cookbook instructions without knowing the objectives of the measurements. For example, A2. The objective of this first item of the table is to observe a simple sinusoidal signal amplification with 10x gain. Your data should be used to assert this claim in the report. Hence, ask yourself if you see, and are convinced that the data presents strong evidence which indeed shows 10 dB signal amplification. Depending on the class, you might have a buzzer in your electronic kit. You can plug the buzzer in with the input signal, hear a weak sound, and then plug it in the output, which gives a much louder sound. That's what amplification means, which you might use every day when listening to music. For step A3, the objective is measuring the gain as a function of the feedback resistance. You should see larger gain with larger feedback resistance, approximately 10x, 27x, and 100x by the circuit design, and this follows the basic op-amp amplification equation. For step A4, it is about output amplitude saturation. This topic has been touched upon in part 1. Obviously, an op-amp cannot give an output that exceed the voltages that it is supplied with. Hence, the output will saturate at the maximum plus or minus as illustrated here. Therefore, in doing this step A4, as the amplitude slider of the wavegen is raised up, we will see the output signal clipped off at the extremum plus and minus voltage level, which is approximately from 1.2 up to almost 2 volt lower than the supply voltages. If you use 12 volt AC adapters, that will be plus or minus 10.6 volt roughly. If you use 15 volt, it will be around 13.6 volt. Observe the sharp flat top cut off in the output waveforms when saturation effect is dominant, such as with 100 gain, and the output may look like a square wave. Step A5 is about gain bandwidth. This is one of the most important concepts. It applies not just to this op-amp circuit, but all things with cause and effect responses. As the frequency increases, at some point, the simple op-amp gain model, as discussed in A3, will no longer be valid because the input oscillation is simply too fast for the op-amp to follow. It cannot, quote-unquote, amplify anymore. The objective of this step is to observe this effect. This will be obvious by plotting the measured gain as a function of frequency, which is also known as Bode plot. An approach to do this step is illustrated in this video. The follow is an excerpt. This illustrates the use of an app to estimate the frequency response numerical figures from the data shown previously. The app first asks to select the data folder, then opens all the files of CSV format, which is the recommended format to save data from the AD to. If all the data files listed are relevant, select Import All. Wait while the app is importing the files, which may take several seconds, then close all the data import windows. Then click Run. It may take many seconds to minutes to run the calculation, and the outcome are two files. One file shows the Bode plot, which shows the decrease of gain versus frequency, and the phase plot showing a change from pi phase difference to only pi over 2 at higher frequencies. The left-hand side is the conventional 2D Nyquist plot. The 3D Nyquist on the right uses the white arrow axis for frequency, and one can see the large gain with pi phase shift at low frequency, which turns into vanishing gain and pi over 2 at high frequency. A table displays the estimates of various quantities from the data. The second output file is simply a record of calculation output from each data file. The graphs shown here are the frequency, amplitude and phase responses, also called Bode plots, of the amplifier, as measured from step A5. The dots are experimental data, the lines are linear interpolation connecting the dots. On the amplitude response plot on the right, the amplitude gains obey the op-amp simple model at low frequencies, but clearly not at high frequencies. For each gain setting, there is a range of frequency, called bandwidth, for which the response is roughly flat. Notice that higher gain is associated with smaller bandwidth and vice versa. This is known as gain bandwidth trade-off. One cannot have both. Either high gain and accept low bandwidth, or have high bandwidth at the cost of low gain. Bandwidth is a concept, not a rigorous quantitative definition. A common convention defines the range where the signal amplitude drops to about 1/2 of its maximum as 3 dB bandwidth. What is the meaning and implication of this? An example will be discussed in Part C, in which the optical signal of a household infrared remote control is analyzed. But here, imagine, suppose you use this amplifier, set at 14 dB gain, for a drone or robot in your capstone project, to process some sensor signals. If the sensor signal frequency is in, say, few kilohertz range around the white dashed line, the expected signal strength will be approximately indicated by the white dot. However, suddenly the drone encounters something that has signal frequency in the high tens of kilohertz range around the dashed yellow line. The signal, as marked by the yellow dot, will be much lower in comparison, and the drone might not be able to detect the object. Hence, it matters to know the working frequency limit of the amplifier as obtained in step A5. As a side note, this op-amp is often called audio op-amp because it works in the human hearing range, below 20 kHz. If you are an electronic hobbyist, you might be familiar with a popular class of op-amps that have few hundred MHz bandwidth for video applications. For example, you might want to shop for an op-amp for, say, video processing. The first thing one should look at is the spec sheets. Since frequency is important for this application, the one thing to check out is the frequency response chart. Each gain has a characteristic frequency response curve, including a 300 MHz resonance for gain of 1. We will learn the concept of resonance in Lab 6. Note that op-amp amplifier is not always about large voltage gain. Often, power gain is important, in which the op-amp is used to drive low impedance loads. Disclaimer: this discussion is not to promote any products. A philosophy of this course is empirical learning. That includes practical knowledge and experience. Hence, this discussion is to encourage you be experienced with practical work, not learning things via abstract theoretical concepts or pedagogical course materials. Eventually, your knowledge will be put to practical use, and the ability to read and understand a product description sheet like this will come in handy. This step A6 is about step response. There are many applications that involve a sudden change. For example, a self-driving car is moving, then suddenly an obstacle appears in front of it. The amplifier response time matters. Recall in the discussion in part 1. If an input voltage changes suddenly, a square edge step, how does the op-amp respond? Intuitively, it cannot be instantaneous. It will take some time for the amplifier to go from one level to another. This time behavior is called step response. If you have learned signal analysis, the Heaviside step function is the integral of the Dirac delta function, and the step response is related to the frequency response of the gain bandwidth in step A5 above, via Fourier transform. Here, the main objective is not the mathematical theory, but an empirical learning of the step response concept and its characteristics. This is an example of a step response. The square wave or square pulse of the AD2 wavegain function can be used for a step function input. This particular example shows the response of the 10 dB gain amplifier shown in the lower right corner photograph. The output, represented by the blue scope trace, shows a ramp behavior. It cannot instantaneously follow the input voltage Vx, but ramp from one level to another over a certain duration. The ramp slope of the response is called the slew rate. It is a characteristic property of the op-amp and the gain setting. The finite time response of the op-amp to a step input is of the same nature as the decrease of response with respect to high-frequency input as in step A5, that is, when the input oscillation is so fast that the op-amp cannot follow. This is a demonstration of the process. As the frequency increases, the rising edge and falling edge come closer to each other. At some point, the output cannot fully reach its maximum and minimum in one cycle, resulting in smaller modulation output, the same effect of decreasing gain at higher frequency in A5. The 3 dB bandwidth of the square wave in this demonstration is practically the same as that of sinusoidal wave in A5. Slew rate is an important figure of merit for those op-amps and amplifiers designed for high-speed response. This example shows an amplifier in the category of high slew rate. It is nearly 1,000 times higher than the slew rate observed in this example. If an application requires a fast step response, the graph labeled settling time provide the relevant data on the rise and fall time. Like the slew rate, the rise and fall times here are in the sub-nanosecond time scale, 1,000 times shorter than the microsecond time scale of the 741 op-amp. Disclaimer. This discussion is not to promote any products, but it shows the practical knowledge of what to look for and how to select op amps for applications that have certain step response requirements. Lastly, a minor but worthwhile additional note about the slew rate is that it is not of the same nature as the time coefficient of exponential rise or fall such as the RC time constant. This shows a comparison. On the left is the typical exponential time behavior with a constant time coefficient tau, its unit is time. On the right-hand side, the dashed slope represents a constant slew rate. Its unit is volt per unit time. Observe how the signal has a constant slew rate slope on the right as the amplitude varies, whereas the equivalent line on the left is not constant, only the time coefficient tau is constant. This is a minor distinction but matters in certain applications. Step A7. Impulse response, which can be considered as the derivative of the step response. It gives another perspective on the time response of the amplifier. Impulse response is the output of a short-duration input pulse that represents a Dirac delta function. Shown here are examples with input square pulses of 1 microsecond and 0.5 microsecond square pulse inputs. If a system is linear, it can be represented as the difference between two time-delayed step functions as in step A6 above. The steady-state responses of the two time-delayed step functions would cancel each other, hence, the impulse response can be viewed as another measurement of the rising edge behavior of the step responses. The part of interest is the tail of the response, which represents the speed of the response, and to be studied as a function of the gain. As expected, there is a correlation between time domain measurements of the response on the left, versus frequency domain measurements on the right. Similar to gain bandwidth behavior on the right, higher gain correlates with slower response on the left. For those who have learned signal analysis, there is an inverse relationship of bandwidth on the right versus time response on the left. Or, one can say that a fast time response on the left corresponds to a wider bandwidth on the right. For a linear system, this follows from Fourier analysis. In practice, the quickest way to get a rough idea of a system response speed is to do either a step response or impulse response measurement. Frequency response, as shown in A5, takes a bit more work and time, hence, measurements like in A6 or A7 are usually done first to adjust or fine-tune a circuit until a certain response speed meets the requirement. And frequency response can then be done for further modeling. This lab assignment is hard work, designed to help you build up skills in circuit engineering that will be useful in experimental projects. What learned here are not restricted to this particular circuit, but general concepts that are broadly useful in general engineering. As the op amp will be used in subsequent lab assignments, experience with the op amp here will be handy later. Last but not least relevant. One should understand that all things physical obey natural laws and can have complex behaviors. For the sake of learning, things are modeled, simplified to help easier understanding. But it is counterproductive if the simplified knowledge are applied, extrapolated without a critical understanding of the complex nature of physical entities and processes. It is worthwhile to make a note about how to select and use scientific technical information on the internet. This will be discussed a little in the follow. This is an example of original scientific literature. At the top is the URL citation. A problem of this type of literature is that it is arcane, for the experts in the same field, and hence not friendly to the general public. This one is even worse in terms of graphic presentation, as it can be ambiguous to identify which curve corresponding to which animal, and the large number of colors are not necessarily distinctive, especially to those with visual color deficiency or impairment. Here are some examples of secondary technical information on the internet. Secondary means it is not of original scientific literature. On the left, at the top is the URL citation. This article and the chart present proper scientific literature citations. However, it would be difficult for a casual reader to see what with all those small polygons as legend icons. On the right-hand side, this article chart is illustrative and easy to grasp, thanks to the chart legends that use animal silhouettes. However, the article does not cite scientific sources, and it is unlikely the authors of the article did those original research themselves. Hence, it can be used, but not perfect in terms of credential presentation. A relevant question to this lab assignment is whether a dog or cat audio engineer would use the same 741 op-amp chip that is popular with human audio engineers. Unlikely, based on their hearing ranges. So, if you are a vet designing hearing aids for dogs and cats, you will need a different chip. Here are some similar examples for the visual spectral response. It is of the same concept as frequency response. Except that the physical stimulus here is the electromagnetic wave in the several hundred terahertz range, hence, it is more conventional to use wavelength, as shown on the right-hand side chart in the unit of nanometer, instead of terahertz. The chart on the right has a proper balance with correct scientific citations as well as informative illustration. Based on the chart, can you tell which animal of the three has the widest bandwidth?